And today we're happy to have Bertrand Eynard from the Institute of Theoretical Physics, Saclay, and he will speak about topological recursion, CFT, and principal bundles in some order. Okay, Bertrand, please.
Okay, so first, thank you, Jan, and thanks to the organizer for inviting me to give this talk. So indeed, the subject of my talk will be CFT, principal bundles on topological recursions. Well, I must tell you, I'm not really a physicist, so what I will call CFT, so which means conformal field theory, will be mostly given by a set of axioms. And you don't need to know any physics to understand that. And the question for mathematicians is, can we find a model for these axioms? And the answer will be with principal bundles on topological recursion. This is work that I have done with Raphael Béliard mostly. Former works also rely on works with Leonid Chekhov and Sylvain Ribot. I have already several papers published with Béliard on this subject, and we are now working on a joint project with Urtubise on Ukasi, and these works are almost finished and will be, I hope, on the archive very soon. So I will first start by setting up the things. So we have a Riemann surface, we have the algebras. I will just to fix notations. I will define what I mean by conformal field theory, so CFT. And this is based on axioms called bootstrap axioms. And then I will show how we can satisfy these bootstrap axioms with principal bundles, and then study things in some asymptotic limit, asymptotic expansion, and we shall solve the asymptotic expansion recursively, and this is called topological recursion. And then I will conclude. So the setup is I will consider conformal field theory on a surface in 2 dimensions, and it will be a Riemann surface. And in fact, in this talk, it will be only the complex projective plane, the Riemann sphere, sigma 0, so CP1. I will consider only that one. And I will also consider a Lie group, a reductive Lie group, on its Lie algebra G, its Cartan subalgebra H, so a maximal abelian subalgebra. And sometimes I will restrict myself to semi-simple or simple Lie groups. So I just recall that at least in semi-simple case, a Lie algebra can be decomposed as a direct sum of its Cartan algebra and the root subspaces, which are basically the common eigenspaces of the commuting adjoint actions of the Cartan algebra. And very often we denote the Cartan algebra as G0 as if it were a root space of root 0. I will also need to introduce the Casimirs. So imagine that you take U in the Cartan algebra and decompose it on a basis, compute in a representation, compute the characteristic polynomial, and it can be written as a polynomial of a coefficient. And this is what I call the nth Casimir. And of course, they depend on the representation, but together the Casimirs generate, the algebra they generate is independent of the representation. Let me fix WLD with some groups, some familiar groups. So GLDC, which is not semi-simple. Its Lie algebra is the set of all D by D complex matrices, and its Cartan algebra is the set of D by D diagonal matrices. SLDC is semi-simple. It is the subgroup with determinant equals 1. Its Lie algebra is the set of D by D matrices of trace 0, and the Cartan is D by D matrices with trace 0, diagonal matrices with trace 0. The roots are diagonal matrices with a 1 and a -1 somewhere on the diagonal. And the corresponding space, so root space, is generated by sparse matrices with only a 1 at some position ij. And if you have a diagonal matrix U in the Cartan, its Casimir, sigma n of U, is just the elementary symmetric polynomial of degree n of its entries. And I also need to compute the scalar product of U with itself. So the norm is just sum of UI, UI. Okay. I will consider two-dimensional CFT, so on our base curve sigma 0, so the Riemann sphere. Just for the specialist, it will be a CFT with central charge equal to the rank of the Lie algebra, so the dimension of H. And sometimes I will denote sigma prime 0 when I remove some points from sigma 0. So what is a CFT for me, for a mathematician? So I mean, we don't really have a good definition of quantum field theories in general. So for us, what we shall call a conformal field theory will be just a set of functions, they are called the amplitudes, that have to satisfy some relations. And so these relations you want to satisfy, you call them axioms, and you call them bootstrap axioms. This is how they are called. Bootstrap means that you can start from nothing. So we will have such functions that depend on many variables. And in fact, physicists have introduced better notations to deal with these functions of many variables. And the notations are obtained with, so let's call them symbols. So you see this bracket here, which contains symbols, is the same thing as this function. So it's just a way to write the function, but recalling that, for example, z i's are points on the curve, where alpha i's are values in the Cartan algebra, and e i's are in the Lie algebras. And they come together, and that's why you denote it with symbols. So V alpha of z, this symbol is called the vertex operator of charge alpha at position z. G of xe is a symbol that is called the current operator of charge E at position x. T of x will be is a symbol called Stress-Energy-Tensor. Wn of x is a symbol called W tensor, and so on. And so what I call an amplitude is just a function from a set of symbols to the set of complex values.
Bertrand, your functions, it's not chiral, it's a full CFT, yes? So they are not necessarily...
I will come to that in a second.
I mean that they are not holomorphic.
This will be in the next...
all right, sorry.
The next thing I'm going to say.
Yeah.
So, and it's just so far it's just symbols, and you have to retain that the order of symbols doesn't matter. What matters is really the nature of the variables, and the symbols are just there to encode the nature of the variables. And also I extend by linearity. So then the amplitude will be a linear map. Indeed, as Jan just observed, I'm going to use also the chiral anti-chiral decomposition. So in fact, all my amplitudes will be the chiral ones. So basically, it's like every function of which is not analytic, you can somehow decompose it on the basis of analytic times anti-analytic functions. So in other words, we are going to consider the complex conjugate z bar and x bars as constants and work only with the holomorphic part. And then there will be something about these coefficientCij's in a moment. So the goal is to find a set of amplitudes that satisfy some axioms. What are those axioms? The first axiom is called vertex current OPE. OPE stands for operator product expansion, but it really just means short distance behavior. So what this equation means is that in every amplitude, when these two symbols appear, and you take the limit x close to z, then an amplitude containing these two symbols is asymptotically equal to the amplitude where you replace the left-hand side by the right-hand side. So basically, this equation, this short distance behavior for symbols, really means short distance behavior of amplitudes that contain these symbols. Same thing. The current OPE is when two currents are close to each other, there should be a double pole. And if you take the sum over a basis of a Cartan, the double pole comes with a coefficient dim h, and then the next two leading order is a finite then you have some O of x minus x prime. And I will give a special name to this finite part, and this is what I will call the stress energy tensor.
Bertrand, when you write the product, what do
Yeah.
you mean actually? Because you insisted that it's just some
It's just
symbol.
two symbols somewhere. So it's just that you have these two symbols somewhere in your amplitude.
Yeah, but v of z product with j of
Yeah.
x or whatever. What this
Well,
product mean?
product just means it's a word made of symbols.
So then you can multiply them at least.
Yeah,
Yeah?
yes. I mean, it's just you put them together in the same amplitude. You just put them next to each other in the amplitude, and the order doesn't matter.
Hmm.
So it just so remember they are just symbols, and what I call products is just that the two appear in an amplitude. Let me continue. So the stress energy tensor is the finite part of the square norm of J taken at coinciding points, but we cannot retake coinciding point because there is a double pole. So after subtracting the double pole, the value of the square norm of J after subtracting the double pole is called the stress energy tensor. This operation of subtracting the double pole at coinciding point is denoted sometimes with this colon notation. Colon, colon. It means take this product and subtract the double pole before taking x prime equals x.
But should at least intuitively some people who know maybe heard something, they should think that these are operators depending on parameters in the bracket. We checked on some whatever Hilbert space and you multiply.
Indeed. The idea is that you would like to realize this symbol as operators in some Hilbert space, but this is not how I will proceed. For the moment, I'm just taking. So indeed, I mean, the goal would really be to find a Hilbert space where these symbols are really operators. And the bracket is really like a scalar product or something like that. But here for the moment, let me present these as just axioms for a set of amplitudes. And similarly, the stress energy, the Wn tensor will be the Casimirs of the J's at coinciding point after subtracting the trivial pole. Okay. Just remark that T is nearly the same as W2 because in the series that are semi-simple, W1 is 0. And just another thing, another remark is that J, you see here there is a dxi. The currents are one forms. And so a current times current is a quadratic form. And in fact, the true nature of T is to be a projective connection. But this is beyond what I want to discuss now. So one of the bootstrap axioms is called the word identities. And word identities is the requirement that whenever you see a symbol T of x, so a stress energy tensor or Wn of x inside an amplitude, this should be a rational function of the corresponding x. Very often physicists write it as d bar t or d bar Wn equals 0. And later, there will be more axioms that are called crossing symmetry and also fusion rules, but I will present them later. So far, what we have. So how do we define a CFT? We want to find a set of amplitudes that are just functions from symbols to numbers that satisfy some these short distance behaviors and the fact that T and Wn are rational inside every amplitude. In fact, those axioms are very powerful because they can really be used to recompute the amplitudes. The big problem is, are the axioms consistent? In fact, physicists have found that with these axioms, you can recompute more or less everything you want, but sometimes you can compute it in many different ways. And the question is, do the different ways give the same result? And this is sometimes an open question. And somehow you have to see if you can realize these axioms with a model that satisfies them. So, in fact, so far I said here that the stress energy it's only the AD case. Let me do a little bit more Lie algebra. So if you take U in the carton, the scalar product UU can be decomposed on the Weil basis of a carton, like that. But if U is in the Lie algebra, you can write it in this way. So there are more terms. So this is still in the, so all these terms in black depend on the basis HR, the Weil basis HR of the carton. But there is an extra term in blue. And just let me remark that in the ADE Lie algebras, every root has norm 2. And so this term is in fact vanishing in the ADE Lie algebras, but it is not vanishing in other Lie algebras, in the non-simply laced. And there is another way of writing this UU in a similar form. I don't want you to retain all the details of that slide. The only thing you need to retain is that you can write the scalar product UU decomposed on simple roots, so the carton part and the Borel part here, in a way such that all the blue part vanishes for the ADE algebras. And somehow there is this 2 minus beta factor that appears. It's like in matrix models. For AD, you have beta equals 2, and this vanishes. But for the others, you can have beta equals 1, 4, and 6 for the algebra G2. So now, in fact, the true expression for T is not what I wrote before. It's this carton part plus the Borel part. That's the full expression now when you are not in ADE. And I just recall that in ADE, this second part can be suppressed. So now I said that conformal blocks, so that was related to the remark of Jan. So in fact, since the OPE and Ward axioms are linear, you can find several solutions, and you can find families of solutions which can make basis. I mean, linear combinations of solutions are solutions, so you can make a basis of solutions. And then you want to find bilinear combinations in such a way that F is univalued, because indeed you can easily understand that that for the chiral parts, are usually they have monodromies. It's impossible to find amplitudes of chiral amplitudes that have no monodromy. It's basically impossible. So, but it's possible to find a bilinear combination for which cancels all the monodromies. And this is basically what crossing symmetry is about. Often in physics, also, you want to find F real. But okay, so now I will concentrate on the OPE onward. And I will realize a model, I will make a model to satisfy these axioms, and starting from connections in principal bundles. Here I will, in this talk, I will focus only on the trivial bundle over sigma 0, CP1. And so I just take a Lie group, and I just take the direct product G cross CP1 with its projection on CP1. We can also do non-trivial bundles, and this is mostly what we do with Urtubis, but it is too difficult for an introduction. And on this bundle, we put a meromorphic connection. So a connection typically like that, where phi of x can have poles of any degrees, and where the coefficients are in the Lie algebra. So it's rational in X with poles and with coefficients in the Lie algebra. And the Fuchsian case is the case where we have only simple poles. And this will be related to our amplitudes by requiring that the poles are the location of vertex amplitudes, and phi I, if you diagonalize it, so every element of the Lie algebra can be diagonalized, so is conjugated to an element in the carton, and the requirement is that the carton part are the charges of the vertex operator. So basically, every time you can find some phi whose such that the phi i's have eigenvalues that are the alpha i's, you are going to realize somehow the vertex operators. When you have a connection, you can study flat sections. A flat section is just a solution of nabla psi equals 0. So it can be written as a differential system here, d over dx psi equals phi psi, where psi of x lives in the Lie group. Psi of x lives in the fiber of the Lie group over x. This psi has monodromies, typically, when you go around the loop. And then you can study the adjoint flat sections. So the flat section in the adjoint bundle, and they have to satisfy nabla m equals 0, which as a differential equation is d over dx of m must be now the commutator phi m, and where m lives in the Lie algebra over x. And in fact, it is known how to solve this equation in terms of psi. Indeed, any solution of this equation for m is the adjoint of a fixed value in the Lie algebra, in the adjoint by psi of x so basically it's a fixed value conjugated by psi. In some way, this is the parallel transport of E using psi. And it has monodromies that are the adjoint of S gammas, of monodromies of psi. Okay, so now let's define the following functions. In fact, they are forms, phi of x dx. It's a one form, but it's defined just as the scalar product of phi of x dx with m of x e. It's just a definition. You can rewrite it in this way. Then let me define W2 as a scalar product of m at x1 e1 with m at x2 e2 divided by a double pole x1 minus x2 to the square, and it's a one-form tensor one form. It's symmetric. Then for any n larger than 2, define Wn in this way. It's a sum of our permutations where you put a scalar product of m with the bracket of m, another m, bracketed with another m, bracketed and so on.
So Bertrand, just to keep in line with the logic, so first you find the solutions, whatever flat sections, and define m, and after that, no?
Okay. I choose a bundle, I choose a connection, I choose a flat section. Okay.
Psi, yeah.
Yeah, psi is a fixed flat section, but every other flat section is equivalent by a Riemann multiplication by a constant. Yeah. So basically, choosing another flat section would just make a conjugation of everything. It's isomorphic.
Okay.
So once you have chosen one psi, you define, in fact, the E means that you define all possible adjoint flat section by varying E.
And after that, you define the amplitudes by this formula.
So indeed, I'm going to define. So far, I'm just defining some functions of x in some one forms of x of xi's. I'm just defining some differential forms, and later I will call them amplitude. Indeed, I will say that they satisfy my axioms. Before doing that, I need to define Wn hat by the inclusion-exclusion principle. So for example, for W2 hat is W2 plus W1, W1. And multiplied by a scalar coefficient that I call tau. And I will say later what tau is. I mean, tau will be defined in the next pages. But it's just a global multiplicative coefficient in front of everything. And indeed, as you said, I will claim that if I define my amplitudes to be equal to this Wn hat, then they will satisfy the bootstrap axioms. This is the claim, and which I will show you in the next slide. So the logic is that we started from a bundle, a connection, a choice of psi. We define those W hats, and the claim is that those W hats are candidates to satisfy all the axioms of all the bootstrap axioms. Okay, so that's what we are going to do now. So let's check the OPs. So let's start with W1. This is the expression of W1, and because there is this phi, and phi has a simple pole at x going to zi, with residue phi I which is adjoint to the charge alpha I, then you can verify that W1 behaves like that near the pole. And if you put that with the exclusion-inclusion principle into Wn hat, you find that Wn hat behaves like that. So which is exactly what we wanted for our bootstrap axiom. And also near a pole where x1 goes to x2, for example, since W2 has a double pole like that, whose coefficient is E1, E2, then using the inclusion-exclusion principle, you can check that any Wn hat has a double pole and satisfies the OPE bootstrap axioms. So the OPE bootstrap axioms are satisfied by this definition. For the word, I will just do an example. Just consider an insertion of a T, which, as I said, is the sum of our simple roots of this expression of W2. So you replace the E1 and the E2 by the Weil basis of the Cartan algebra, plus this product of W1 plus this 2 minus beta term, which is there for non-AD algebras. You compute all that. It's a bit of work using the properties of psi, using the differential equation of psi and everything. And you realize that this is equal to the scalar product of phi with itself. So it's a rational function of x. So the word identity axiom is satisfied. And you can do the same thing with any other inclusion of T, more currents, more Wn, and so on. But the equations will be more complicated. But believe me, the word identities are satisfied. So, as I said, there is something missing in my so far. It's this global coefficient, which I noted tau, and it's the tau function. How do we define the tau function? We have to rely on what Goldman did more than, I think, 30 years ago. But Goldman did it for non-trivial bundles and with a holomorphic connection rather than, basically with connections which don't have poles. But let's redo what Goldman did with poles. And it doesn't matter if the bundle is trivial or not. Let's consider the homology of sigma 0, where I remove the poles, into the flat sections of the adjoint bundle. Let's illustrate it as follows. So take a Jordan loop in the base or Jordan arc in the base, and you lift it to a flat section. So in other words, you start from an E and you follow it along gamma by parallel transport. And then you take linear combinations of such classes of Jordan arcs in flat sections on such that the boundary is zero. Boundary is zero means that over the boundary of every gamma, the sum of all the e's in the fiber should be zero. So this is what was defined by Goldman. And this is also exactly what you need to integrate W1 such that the integral is well defined and is invariant under homotopic deformations of the contours. Inside this space, because we have these poles, we have poles at zi's, there is a trivial subspace, which is you take a small circle around zi, take an E in the normalizer of the monodromy around zi, and this is clearly, then this is clearly a closed loop inside the bundle. And so it's a subspace of H'1. And it has dimension the rank of the Lie algebra. Now let's write the full H'1 as the sum of these trivial subspaces plus an H1, so a supplementary, and whose dimension is to this number, which is even, in an even number, and which was the dimension computed by Goldman. So this makes H1 a symplectic space, where the symplectic form is the intersection. To compute an intersection, you just take the intersection on the base and multiply it by the scalar product of the e's in the fiber above the intersection, and then this defines the Goldman intersection. And now choose the Lagrangian decomposition of H1. For that, we shall choose some cycles, A1 to AG hat, on which the integral of W2 vanishes. So in fact,
these are kind of modulo this Lie algebra data. Your cycles has boundaries in the marked in the removed points. Yeah,
no. They are really closed. I mean, in H1 they are closed, and I will come back to that. In H prime 1, indeed, you can have. I mean, I will talk about those that terminate at the zi's later. For the moment, they are not above the zi's. They are really closed loops.
Okay, all right.
And the dimension is finite, and it is 2G, plus those trivial cycles around. So in fact, those are loops around the zi's. They do not end on the zi's. There are loops around the zi's. And now, so we choose Lagrangian decomposition, meaning that we can choose arbitrarily some B1, Bj with symplectic intersection with the AIs. And the Bj, the B's, they make a Lagrangian. And it's just up to our choice. To define the tau function, indeed, I will also need to integrate W1 on paths that can end at the zi's. But you see, I want to integrate from some reference point, let's say x0 to zi, but I cannot integrate W1 because it has a pole at zi. But I can subtract the pole, integrate, and then re-add a term that somehow cancels the dependence in x0. And this is what I will call the generalized integral of W1, but now which ends at zi. Okay. And this is how I define the log tau. Tau is 1 over 4 pi I, the sum from 1 to g of the A cycle integral of W1 times the B cycle integral of W1, plus this extra term, which contains integral that end at the zi's. If you remember that when you consider the integral around the zi's, you in fact compute the residue, and the residue is the charge alpha I. You can reinterpret this term somehow as similar to these terms, where the A cycle will be played by the role of the A cycle is played by the small cycle around zi, and the role of a B cycle is played by a path ending at zi. So somehow this is why I call them generalized cycles, because they are not cycles, they terminate at zi. But this defines the tau function. Why do we define tau function in this way? It's because it has beautiful properties. So this is my definition of tau function. It has beautiful properties. In particular, under deformation of a connection. So deform your connection, which means deform phi, your connection field phi. This induces a deformation of your flat section psi, and the two are related by the Lax equation, as usual. Then the theorem is the following. There always exists an element in H prime 1 such that this F delta, this which is the deformation of psi, which is the Maurer-Cartan, if you want, the Maurer-Cartan form of the deformation of psi, can be written as such an integral with some x on some rational function. The way to prove it is just you write Cauchy residue formula for F delta, move the integration contour to the boundary of a fundamental domain, use Riemann bilinear identity on the monodromies, and you will find this. And where gamma delta, in fact, when you do that, you realize that gamma delta is a sum of arcs, Jordan arcs that are the edges of your fundamental domain, weighted by an element of your Lie algebra, which is the deformation of the monodromies. Okay. This implies, and then the theorem also says that now the deformation of W1 is the integral of W2 on this gamma delta. And more generally, the deformation of Wn is the integral of Wn plus 1 on this gamma delta. And also, the deformation of log tau is the integral of W1 on the same gamma delta. If you want, let's consider these coordinates AI that are the A cycles integral of W1. If you want to make a deformation of phi that deforms only AI, So basically, you want to compute d over dAi. Then you will find that using this definition of tau and using this theorem, you will find that the deformation of log tau, the derivative of log tau with respect to AI, is the B-cycle integral. So basically, this is Seiberg-Witten equations. So our tau satisfies our log tau is a solution of Seiberg-Witten equations.
So it's a pre-potential for some integral.
Yes.
Yeah.
Yes, basically. Yes, so this is why it was useful to introduce it. And what I claim is that this is the good prefactor to have in front of our amplitudes. And so indeed, to define conformal blocks, remember that for each choice of connection, on the set of bundles of paired bundle connection is called the DeRham moduli space, but here I take the DeRham moduli space of connections with given poles on given charges. That's why I write the Zi alpha i's here. And remember that P is in fact the trivial bundle, so you vary only the connection here. Then for each sub-choice, we have an amplitude that satisfies the axioms. And now we want to find some bilinear combinations where we somehow we eta here is eta is I mean each eta is one choice of connection, and you have to take such a sum such that this will satisfy the crossing symmetry. I will not insist on that, but I'm just claiming that this is possible. And this strongly relies on how log tau changes under change of Lagrangian. And it changes with the generating function of a change of Darboux coordinates in integrable systems, but I don't want to insist on that. Okay, now let me move to, well, let's first talk about the generalization to the non-Fuchsian case.
Bertrand, but let me just kind of summarize. So if you consider your M, this M, it's a moduli space of this, so your conformal blocks form what, bundles with connection of the moduli space geometrically?
Yeah, yes. Okay, I suggest we discuss that later because it's beyond my scope. So
it's up to you.
For the moment, I compute just amplitudes corresponding to one point in this moduli space.
Okay.
And indeed, now the thing is to put them together to construct really the CFT amplitude. So, but let me first go to the generalization to the non-Fuchsian case. So far, I talked mostly about the case where phi has only simple poles. And what happens when there are poles of higher degree. So remember how we define the Goldman cycles. So we had the Goldman cycles, which are really truly closed cycles. Then we enlarge a little bit with cycles somehow ending at the simple poles, the dies. And what happens when you have higher order poles? And let me recall that the good thing with these Goldman cycles is that this is the natural set of things on which you can integrate W1, or in fact on which you can integrate any meromorphic one form that has the same monodromies of W1. So let's define this space of meromorphic one forms, generalized meromorphic one forms. Let's call them, I don't know. I mean, I don't know a name for that, but which is the H1 of sigma 0 with the poles removed into flat sections tensored with the canonical bundle with poles of any degrees. And somehow, in some sense, this is the set of locally meromorphic one forms that have these monodromies, so the same monodromies as W1. And we would like to define the generalized cycles to be the set of cycles on which you can integrate such forms.
So star means what? Poles of arbitrary order?
Arbitrary degree, yes.
Yeah.
So, yes. So now we'd like to define the generalized cycles as things which you can pair, I mean, on which you can integrate these omegas. So on which you have a pairing, a good pairing. So we shall start by defining the cycles as a subspace of a dual of these one forms, a subspace of a space of forms that have those modules. And how do we, but we shall not take the full dual. The full dual is something rather horrible. But let's take the subspace of a dual that satisfies some constraints. And the constraint is that when you integrate, when you pair not with W1, but if you pair with W2, you want that the pairing with W2 have those monodromies. So this is the requirement. And you can check that H'1 is a subspace of M1 in the Fuchsian case. And also I will use the Poincaré notation for the pairing, as usual. So I mean, I will write the pairing as an integral. Even though gammas are not necessarily cycles in the usual sense, but they generalize cycles, and so I will write the pairing as an integral. So the previous case on the Goldman cycles are special case are subspaces of this M1, but this is more general. And now the tau function in the general case, where you have a connection with poles of arbitrary degrees, can be written in this way. So you have this usual holomorphic, this Goldman cycle part. The generalization with respect to the, where here you have, so since the alpha i's are the residues, this is what you have for the simple poles, and you have more terms that correspond to, that are obtained by finding a Lagrangian decomposition for the higher order poles. I don't want to go into the details, but basically every Lagrangian decomposition of this M1 will give a tau function. And it satisfies the same deformation properties. So for every deformation of your connection, but now you can deform higher order poles, there exists a gamma delta in M1, such that the deformation of Wn is the integral of Wn plus 1. And the converse is also true. For every generalized cycles, there exists a deformation such that the deformation of W1 is indeed the integral of Wn plus 1 on that cycle. And the same holds also for log tau, except that you have to choose your cycle only in the Lagrangian for this to hold for tau. This holds, this holds for the Wn's for any gamma, but for log tau, it holds only if gamma is in the Lagrangian. And in fact, this defines a map from these generalized cycles to deformations. And let's call it the Goldman map, because this is what Goldman did for the holomorphic connections with no poles. But here we generalize it to connections with poles. And Goldman already noticed that if you push forward the intersection form, you get a symplectic form on the tangent space, which is called the Goldman bracket, the Goldman symplectic form. Okay. Okay, that was mostly all for this bundle part. And indeed, as Jan noticed, there are many open questions and you would like to go further. But now let me skip to computing everything as a formal series. So this is called heavy limit. Heavy limit means that we rescale all the charges to big charges. So basically we rescale all charges alpha I to 1 over h bar alpha I, where h bar is a small parameter. So the charges become large. All our amplitudes will now be functions of h bar. And in fact, we shall study them in the asymptotic, as asymptotic expansion as h bar goes to 0. And we shall construct all the amplitude and conformal blocks as h bar formal series. In fact, I should say trans series, okay, because there will be exponentials as well. And the idea to reconstruct these series and trans series explicitly is to solve the word identities order by order in h bar and find a recursive procedure. And this is basically what topological recursion is. It's the recursive solution of word identities. Let me see what it means to take the heavy limit for the connection. When you take the heavy limit, basically you rescale phi into 1 over h bar phi, but the coefficients can still depend on h bar, and the leading term, phi of x h bar equals 0, is what you call a Higgs field. and it's a rational section of the adjoint bundle, tensor 1 forms. And the Higgs field, you can diagonalize it. So basically every Higgs field is conjugated to a diagonal matrix. So matrix.
No. I mean, it's of course it's an assumption. You
locally,
cannot.
it's locally.
No,
locally
you can.
for,
You can. But no, I'm
okay,
confused. But if it's nilpotent.
Yeah, indeed. So, but it's not nilpotent for every x. Typically, so in some open.
No, it can be
Okay.
nilpotent for every
Okay,
x.
indeed. I should have said that. Okay, let's say we restrict to the case where it's not nilpotent. And let's say that generically, for in many, I mean, I just want to simplify the discussion. Let's focus on the case where you can do it. So, in fact, indeed, this is not necessary, but I thought it would make the presentation easier. The thing is that V is not, so is also a section of a bundle, but it's not the same section as psi. It does not satisfy, it's not a flat section for the same connection. It does not have the same monodromies, and in particular, since V is algebraic, its monodromies are generically in the value group. And the WKB asymptotics of psi is basically that psi starts with V times e to the exponential of 1 over h bar times an integral of y. So this is the standard WKB asymptotics. Indeed, for the nilpotent case, you have extra complications, and I want to ignore them. Okay. And when you do this asymptotic of psi, you can compute the asymptotic of W1, and you remark that W1 starts with order h bar to the power -1, and the first term is just the scalar product of y with e. Okay, plus an h bar expansion. I will need something which is the definition of branch points. Branch points are points where there is a root that annihilates y of a. And if you want in GLN or in SLN, this just means that two eigenvalues of y coincide. So the branch points are the places where two eigenvalues become equal. So this will be useful. Now, what is the spectral curve I'm going to talk about? So yes, so the spectral curve is just this y of x. So basically, it's the set of eigenvalues of the Higgs field. So it's an algebraic curve that you can obtain by writing that the determinant, the characteristic polynomials of the Higgs field is vanishing. You can do that in a representation, and I will come back to that later. But basically, this is an algebraic curve, and it has a certain topology, it has a certain genus. To understand on why dx is a one form on this algebraic curve. And typically in our Fuchsian case, y dx has n times d simple poles, where d is the dimension of this representation, at the zi's, and whose residues are the coefficients of alpha I on the diagonal. To understand the topology of this spectral curve in the SLD case, there is a kind of mnemotechnic trick. Take a graph, a trivalent graph with n legs corresponding to your n zi's. Then make d copies of the same graph. Then fatten the graphs into a surface, and this will be your surface. And basically the genus of that surface is the number of loops in your graph here. And you can compute that the genus is that, and it is exactly half the dimension of H1 H prime computed by Goldman. It's not of course by accident. And you can also compute, so if you choose some A cycles, typically here, you can compute the periods, and they are called in CFT language, they are called the intermediate charges. So for each choice of Higgs field, we have, which we can label with the pairs. So for each choice of Higgs field, we have a spectral curve. And for each of them, we shall build some conformal blocks, a solution of the actions. And also here, since I take this determinant, it means either I'm in the algebra SLDC or GLDC, or I have chosen a representation, and I will show how to go beyond the SLDC case. So when you are not in SLDC, you can either take a representation and you can represent G in some SLDC and get some spectral curve, or you can also work with something called the cameral curve, which then does not depend on a representation. And in fact, with Urtubis and Béliard, we are developing topological recursion on cameral curves, and this will be shortly published, I hope. So I will skip this slide, but just let's say that the SLDC case is already solved. There is something called the topological recursion that has been existing for nearly 20 years now, and which was in fact exactly the solution of the word identities for SLDC. And I will skip this slide. Okay. Yeah, so this one as well. I will move directly to the case of general simple Lie algebra. So let's take a simple Lie algebra, so either A, B, C, D, E, F, G. And I gave you before the expression of Wn. Remember, Wn was a sum of scalar product of some m's with some commutators and so on. And if you know the asymptotic of psi, you can compute the asymptotic of Wn, and you see that they have an h-bar expansion. Formally, if you plug the WKB expansion of psi, you get formally an h-bar expansion for Wn. And this expansion started at -1 h-bar to -1 for W1, but for all the others, it starts off at h-bar to the power 0. And in fact, to be honest, if you get an h-bar expansion only if the EIs are in the Cartan subalgebra, but if EI is in some root space, GRI, you have also an exponential factor with e to the h-bar -1. So in fact, this is really a trans series. Okay, like WKB in general. Just let me notice that if your algebra is A, D, or E, and the E's are in the Cartan, then in fact, the only non-vanishing term in that sum are those for which chi is of the form n-2 plus 2g. So you recover the usual topological expansion with h-bar to the 2g minus 2 plus n. Yeah. And also in case where the connection phi, the Higgs field phi, the Higgs field phi corresponds to a Drinfeld-Sokolov system and the E's are in the Cartan, then also chi starts with order n-2. But in general, otherwise, for BC, FG, or E's not in the Cartan, you only have this. So now our goal is to compute the coefficients of Wn order by order in h-bar. And we know the initial terms. So for k equals -1, we have W1 -1, which I already computed in the previous slide, and which is just the scalar product of y with e. Good. At order k equals 0, you can compute W1 0. It contains the Maurer-Cartan form of V, plus a term containing the first subleading term to the Higgs field in the connection. Okay. W2, the leading term is this expression. So remember that W2 was the adjoint of psi E1, psi of x1 E1, and psi of x2 E2. So here I just replace psi by V. Basically, I just keep the leading term in the WKB. On more generally, for Wn, the leading term is just obtained by the same formula, but you replace the m's by the adjoint with the leading term of WKB, so V. So this is it. So basically, we know all the terms with k equals -1 and k equals 0. Now, how can we compute the next two leading orders for these WNs? And there is a recursion. Let me write the recursion as follows. So this is a formula. And what you have to see in this formula is that the left-hand side, to order chi that you want to compute, is expressed in terms of other w's which have lower chi in the right-hand side. So this is really a recursive formula. It contains the sum over all branch points and residues at the branch point of some kernel whose denominator is the root of y of z, so precisely which vanishes at the branch point. And remember that in SLD or GLD, this just means the difference of two eigenvalues. And you have these terms in the bracket, which are familiar in topological recursion. But in ADE, you have only the black terms, and in the overlay algebras, you have also this term, which is proportional to 2 minus beta here, and so which vanishes for ADE, but which is there for all the other algebras. And notice that in ADE, the algebras, here, if you take all the E's in the carton, this closes. But if you are in BCFG, you need some terms that are not in the carton. So you need the Borel part. Basically, in non-simply laced algebras, the topological recursion mixes the carton and the Borel. But in ADE, they don't. And so when you are not in the carton, if you are in the root space, you need an extra equation, which is just that one, and I don't want to comment on that too much, but the idea is that this is the solution of word identities. This is the recursive solution of word identities. So it's a constructive way of finding solution to word identities. So the conclusion is that so in fact, I finished my talk. My time is over, I think. Let me summarize. When the charges are finite, we can realize a model of the bootstrap axioms by taking a bundle plus connection. And from this, we can, we computed a flat section on the adjoint bundles. We define some functions wn and wn hat. And the claim is that they can be used as amplitudes. So they are solutions of OPE and word identities. And there is a way to make them also solution of cosine. The heavy limit consists in doing the same thing in a WKB asymptotic series. So you decompose Wn as a formal series or trans series if the E's are in the Borel. And they obey a certain topological recursion. And they satisfy OPs and word identities almost by construction. And also, in the process, I showed you that we can compute an explicit expression of a tau function, which will automatically satisfy Seiberg-Witten, but also Miwa-Jimbo on Bertholin-Lagrange equation. And usually, when people define tau functions in integrable systems, usually they define them as solution of some differential equation. Basically, very often you can define only the differential d log tau. And here we really have an expression to compute tau directly, pointwise computation of tau. We do not rely on deformation equations, but we prove afterwards that indeed tau satisfies the good deformation equations. Also, the generalized cycles played an important role in constructing tau. And in fact, this is related to your remark, Jan. You can use the space, so this vector space of generalized cycles, you can use it as your Hilbert space if you want. And then the operators are really, so typically the vertex operators in the Fuchsian case are really the exponentials of these tangent vectors, so the exponentiated tangent vectors that end at the zi's. So you can reconstruct the vertex operators. Now they are not only symbols, they are really operators acting on that Hilbert space. And same thing for currents and everything. And in fact, in the non-Fuchsian case, you can use the same definition for an arbitrary cycle, define e to the d gamma and call it, I don't know, something like a generalized vertex operator. And it will have more complicated OPs than in the Fuchsian case, but still it deserves the name vertex operator. Basically, you can build irregular conformal blocks in this way. And it's more or less, I mean, in this construction, this doesn't make really a difference. Also, I discussed here all the algebras because all this, in particular, the topological recursion, so in the past was done only in the GLD and SLD case, and now we have generalized it to all the algebras. Also here, I was considering only trivial bundles. Trivial bundles already have plenty of applications, in particular all random matrix theory, KDV, KP, and many applications to topological strings are obtained with trivial bundles. But in fact, we can also do non-trivial bundles, and this is mostly what we do with Jacques-Curtubis, and we can also use chimeral curves. For the prospects, there are many open questions that I think probably come to your mind, but let me just mention a few of them. So I did not study the fusion rules so far, and this is not even in the work in progress. So fusion rules is really some axioms that we need to check. Also, all this construction was when the central charge takes a very specific value. And in fact, all this formalism can be also generalized to other central charges. And also, there are many other works that carry similar ideas, like the works of Lizovic, Gavrilenko, Marigno, Iwaki, Bertola, Korotkin, Bridgeland. I mean, many other works are related to what I talked about, and it would be really interesting to remake a dictionary to their approaches. And I thank you for your attention.
Thank you very much. Are there any questions? By the way, where did you use that your central charge is a dimension of Cartan?
It was when you write the Stress-Energy-Tensor as the square of J. If the central charge is not that value, then the Stress-Energy-Tensor should be something like J square plus Q dj.
Okay. And I assume that you can work with other initial curves than CP1.
Oh yeah, yes, of course. This is what I mean by non-trivial bundles.
Yeah.
In non-trivial bundles, I also mean non-trivial base.
I see. And yeah, since you mentioned this in the link to other papers, some of them maybe I know something about. So that the question is that you have this heavy limit and finite charges. If you in the heavy limit you use formal WKB expansions, but you can use the exact WKB analysis and make it analytic. So will you have sort of a holomorphic family in H bar?
It's also some work in progress, and in particular, I think the more advanced on that is Raphaël Béliard. He really, I don't know if his paper is already on the archive, but he studies this question in detail. So basically, he uses the Borel transform.
Resurgence properties of
resurgent.
conformal
So basically,
blocks.
he proves, at least in some cases, that this is resurgent.
Yeah. Okay. Yeah, actually very interesting. So it's kind of the way to solve conformal field theory.
Just one other way.
One possible way without representation theory, as you know, in the early 80s, just by pure analysis and some geometry. Okay, well, it's great, really interesting. So last chance to ask questions, our speaker. Well, if there are no questions, Bertrand, thank you very much. Very interesting talk. And this is it for today.